Hi, back for part 2 of chapter 19. So in chapter 5, we talked about delta H, and we said that delta H can be measured with the method of calorimetry because, as we know, that Q is equal to delta H. So Q of a reaction is also equal to delta H of a reaction. So that is just a simple method of measuring delta H. But there is no similar method for measuring the delta S. But it can be calculated from standard molar entropies. So there are a couple of rules that you have to remember when you're doing the calculation. Elementals are not zero, unlike when you're calculating delta H. The standard S of a gas is greater than the standard S of a liquid and a solid. Your standard S values, again, S is your entropy, increases with molar mass, and your standard entropy also increases with increased number of atoms in the formula. So those are just some handy rules to know when you're making a judgment about the delta S's. So we can use this equation, which looks so similar to the one that we used for measuring delta H from standard heats of formations, but this is standard entropies. And so the change in entropy, the delta S, for the overall system, all right, so this is all about the system, and the system would be the actual reaction that's occurring. And so to find that, you would just use that same table that you used for finding delta H's, but there's a column for entropy, and it's that Greek symbol for sum of, SUM, of the S's of the products minus the sum of the standard entropies of the reactants. So the same format for the formula, it's just you're pulling your numbers from a different column. So if the reaction that we're looking at is the synthesis of ammonia, nitrogen, hydrogen combined to form ammonia, then I would just use the 2 times the value for ammonia from the table minus 2 times the value for nitrogen plus 2 times the value for hydrogen. Sorry, 3 times the value for hydrogen, and I made a mistake here. That should be hydrogen. Okay, so again, products minus the values, the sum of the values for reactants. And so I look those values up on that table, and I plug my values in, and I calculate the value of negative 198.3 joule per Kelvin. So the units on the table are going to be joule per Kelvin. And so we calculate out a negative number, and that negative number is consistent with how I would predict it to be based on the fact that I have the formation of fewer number of moles of gas on the product side than the total number of moles on the reactant side. So it becomes less disorganized, and my delta S value is negative. Okay. So we also want to be able to calculate the entropy change for the surroundings. So the delta S for the system, as I said before, is calculated from the table values. So in my example, the system was my reaction between nitrogen and hydrogen, and I showed you how to calculate that. But now what we have to do is figure out how to calculate the delta S of the surroundings. and it depends upon the amount of heat gained or released by the system. So what I would have to do to find it for the surroundings, I would take Q of the surroundings, which is equal to negative Q of the system, just like we said back in chapter 5, that the surroundings is always opposite the system. And so the delta S of the surroundings ultimately is going to be equal to negative delta H of the system divided by the temperature. And so I calculate my delta H using that equation for the reaction between nitrogen and hydrogen. Just like we did back in chapter 5, I get my value. I then use that value, my delta H value. I'm going to use it here in this equation, and I'm going to change the sign because remember, the delta S of the surroundings is going to be calculated using the negative delta S of the system divided by the temperature. So I plug that in, I do my little bit of mathematics there, and I calculate 310 joule per Kelvin. So then, in order for me to calculate the delta S of the universe, which is ultimately what I'm trying to do, I take the delta S of the system, which I calculated on my last slide, and I add the 310, being careful that my units are the same, the 310 joules per Kelvin calculated from this formula here, and I get an overall value of 112 joule per Kelvin. I see a positive delta S. That means that this process is spontaneous because the delta S of the universe, that's the ultimate determining factor here, what the delta S of the universe is, that value is positive. Okay, let's stop there.